Admin here. We are going to go over the chi-square distribution for tables. So starting in 2027, they have dropped the first part of the chi-square, which is goodness of fit. That's not going to be taught. So it's actually going to be a fairly quick chapter. We're just going to do tables. So day one is an introductory day. So we're going to go over all the little things that you need to know about this that could show up possibly in multiple choice. Okay. So the chi-square is for tables. Okay. The smallest you can have is a 2 by 2 here. It's got to have some dimension. Can't be a by one, like 6 by 1 or 1 by 6. It's got to be at least a 2 by 2. So here's the smallest you can have. So the chi-square for tables has on Desmos, if you type in the word inference here, it they dropped this goodness of fit for the 2027 test, but for 26 it's there. So they just have a chi-square test for independence, but technically there's two different kind. It's the same math, but they're two different names: independence and homogeneity. Okay, which are spelled right here. Okay, so the difference is in independence. So in the independence one, um, oops, the it's one population and two traits. And by the way, this is really hard to figure out sometimes. I see this as a group of voters, one group of voters. And then you got male and female, two traits, their gender and then their political party preference. And so I'm wondering, is gender independent of that? This is actually the HA statement. The question is always HA, by the way. Okay. So I wrote that here. So is gender is independent of political party affiliation or gender is dependent. A lot of times they'll use the words same and different. So they would join the political party at the same rate and they would join the political parties at different rates. Very hard to write with this. Different. There we go. Okay. It can be worded a lot of different ways, but same and different is kind of the most common. Okay. So, some little things you should know is these are the observed data. You have observed data, and then, of course, you have expected data. And expected data would be if the data is the same. If HO is true, what would be expected from this table? It's very easy to calculate. So this, you got to get the table totals, 125. This is 110. This is 75 at 150, 145. And then this is 130. And the total, as you can calculate, is 255 to 5. And how you get the expected values, the general term is it's take the total here for this one, the expected will be 125, the total here, times 110 divided by 255. So let me redo that on a side calculator. So I don't gotta go to Dismos. It'll be 125 times 110. Then you're gonna divide that by 255. Okay. And that comes out 53.9. So 53.9 here. Okay, 53.92, actually, if you go a little further. For this symbol right here, I'm going to go 130 times 110 divided by 255. So I'm going to go 130 times 110, enter, equals, divided by 255. And that comes out 56.1, basically. 56.1. And then this one right here, how you do this one would be 125 times 145 divided by 255. So I'm going to go 125 times 140, try again. 125 times 145 divided by 255. Like 71.1. The last one would be for 70 here would be 130 times 145 divided by 255. So we're going to go 130 times 145 divided by 255. Okay. Try that one more time. 130 times 145 equals, and divided by 255. You get 73.9. Okay. Now, that's the expected values. So you got to get the expected values. Then you got to get the chi-square terms. There are 4 terms here. The chi-square is O minus E squared divided by E. Okay. So in this case, in this one right here, it'd be 50 minus 53.9 O minus E squared divided by the expected 53.9. Okay. You're going to get those 4 chi-square terms, add them up. That is called the chi-square sum when you're done. Now, let me clear all this, okay? We're going to do this over and over, but what's cool is on Desmos, it goes it's pretty easy to do. Okay, so let me go back to Desmos here. I'm going to go chi-square for independence. Yeah, it says independence, but it could be either test. Okay, so you're going to type in the the numbers. Okay, so back to this: 50, 60, 75, 70. 50, 60, 75, 70. Okay, we're going to go create test. Now, what's kind of cool is you can do this first. You can get, isn't that great? The expected sales are calculated for you right here. Isn't that awesome? Right there in parentheses. It's the same thing that I did by hand, but you didn't know how to do by hand in case that comes up on the test. But now the chi-square contributions, okay. What this is this tells you how large the discrepancy is. So these two have a larger blue area, meaning the chi-square term is larger. If you want the totals, by the way, you can get that. That's just the numbers on the side. That's kind of cool to have. Okay. So these two contribute most to the chi-square sum. Okay. Then if you want to run the test, which we'll do later, the test is skewed to the right. Even though it is not equal to, even though it's this, it's always skewed to the right. And it actually looks like this. This is a bad drawing of it. The degrees of freedom is how many rows you have minus 1, and then how many columns you have minus 1. And since this is a 2 by 2 table, it's 2 minus 1 times 2 minus 1, which of course comes out 1. That's why you have the degrees of freedom of 1. This comes out a p-value of 0.321. This is your test statistic. This is similar. The other test statistics we've had have been, we've had a t-score and a z-score, correct? That's been the test statistic. And this is another test statistic. The chi-square sum is a test statistic. And then it gets turned into a p-value. The larger the chi-square sum, the smaller the p-value. Because the bigger the chi-square gets, that means it's further and further away from the expected numbers. And then it'll drop the p-value a lot lower. So this is 0.321. So we're not really trying to get into that a whole lot just yet. I'm just trying to intro all this to you. Okay. All right. So let me go back to this. All right. So we're not going to do this other one so detailed. This is a test for homogeneity. Again, Desmos calls them all chi-square. Let me type it again. Inference. Remember, we've done two types of t-test, well, actually three. We've done a t-test, a paired t-test, which is just a regular t-test, and we did a two-sample t-test. And then we've done two types of z-tests for proportions, one meaning for a single proportion and one for two proportions. Now, this is the table one. They call it for independence, but it could be either one. Okay, the other one is the homogeneity one. You're wondering, you have two populations in one trait. I think of these populations as different, Gen Z, millennials, Gen X, and of course, where they get their news, right? Obviously, Gen X, the oldest one here, is going to get their news from the print media the most. Gen Z, the current kids, are going to get it from the social media the most. Okay. And here's the totals again. So we could type this table in just as easily and run the test as well. Okay. So here's your HO. There is no association between the age group and preferred news source, and there is an association. So up here we used dependent and independent because it was test for independence. You could still write this with the word independent. You could say age group is independent from preferred news source, and your news source depends on what age group you're in. You can still write the same. Okay. There's no symbols on this. There's no X bar and P hat. It's just words. Okay. But HA means different. HO means the same, and it's considered a not equal to test, even though it's going to be skewed to the right. Okay, the distribution. Okay. So in the end, how you end up running this test is you've got to go through HOHA. Your requirements are pretty simple. So we can touch on that a little bit. The requirements are still SPIN. Okay. So let's talk about the SPIN acronym. Same old thing, representative sample. The population should be 10 times the sample size. So here's the sample size. So 6,000. Everybody in the table is independent. The N in SPIN is not about normal because the data isn't normal, it's skewed to the right. The N in SPIN stands for you want the expected values, not the observed values, but in this table right here, you want of those 9 cells, you want the expecteds to all be bigger than 5. The expecteds to be bigger than 5. Okay. Now, if 1 or 2 isn't, the technical rule is 80% of the expected cells need to be bigger than 5. Usually they all are. Okay. So then once you establish the assumptions, HOHA assumptions, running the test is pretty simple. So let's go ahead and run the test. This is practice. So we're going to do this in subsequent days, but you can kind of see it. Okay. So running the test will be easy. I got to get these numbers in there. 150, 30, 20. All right, here we go. Let's try this. 150, 30, 20. Go to group B. Let's see here. And that's 100, 70, 30, 100, 70, and 30. And then the next one will be 50, 100, and 50. All right. 50, 100, and 50. Okay, we're going to go create test. And I'm going to go ahead and get the expected cells first. Now, it's really important that you write this out. So when you are doing the SPIN acronym, and you get to the N in SPIN, you're gonna write the expected cells out. Usually you write them in the table, but you may have to make a quick little table. This is a 3x3, right? And then put the expected cells in there and say, see, all the expecteds are bigger than 5. Don't just say it, actually write them out. So you actually end up running the test and you see all the expecteds are bigger than 5, right? There's 33, 66, and 100. So that makes sense to you. So those are all bigger than 5. So we have enough of that. The contributions is kind of cool. You can see that this middle row is coming in exactly as expected. And then group A has a couple of them that are very different than expected, and group C has one that's really different than expected. Because you can do the chi-square, the term for each one of them. It would be observed 150 minus 100 squared divided by 100. You could get the term. They don't have those here. They have totals. They put the totals in there. So those are the totals for the call and everything. Okay. Then if you run the test, by the way, there's no confidence intervals. You run the test. There we go. The p-value is really small, so there is evidence here. So you would draw this curve out. You know, the degrees of freedom is 4 because it's 3 minus 1 times 3 minus 1, which is 2 times 2, which is 4. Okay. So when you get there, the degrees of freedom is 4, p-value is tiny, and the chi-square sum was 101. So remember, so when you finally get to draw on the test, you would do that. Chi-square sum is 101. P-value was less than 0.0001. We're going to circle that, put a little dot there. Okay. And then we have a reject HO. We do have evidence to suggest that different age groups use different platforms for their news. Pretty simple. That's how you run that. It's very, very easy to do. So that's kind of just, we're just kind of doing the basics today. We're not really getting into the nitty gritty. I'm doing it, looking ahead a little bit, but so here's another prompt like that. Okay, same thing. So which one would this be? So we're gonna name the chi-square type, write a pair of HO and HA, calculate expected values, and write inputs in the table. We would do this. Let's do this all together, okay? Is the effectiveness of the 3 brands of preventive medicine the same across all the categories? All right. So this is to me, this is one group, doing something, having 2 traits, full brand A and full relief. So this would be probably a chi-square test for independence. Okay, so no, I'm sorry, homogeneity, because I think it's one population and 2 traits. Yeah, it's just one group of people taking medicine. The 2 traits of the brand they took in this. So HOHA is there is no difference between the brands and the relief status, and HA is there is a difference between the brand and the relief status. Pretty simple. So when you start doing the requirements, you got to type all these in. So requirements is the SPIN acronym. So SPIN, representative sample, population is bigger than 3,000 of people that take the medicine, independent. In the end, we've got to show up to see if all of these are bigger than 5 or 80% of them. So this is another 3 by 3 table here. Okay. So let me clear that. Let me type these in. Get rid of this. So type in inference. Okay. And we're going to go 60, 25, 15. 60, 25, 15. 45, 40, 15. 45, 40, 15. And the last one is 30, 50, 20. 30, 50, 20. Okay, great test. 50, let's get the expected data, the contributions, totals. All right. So if you're looking at this, there's the expected, all the expecteds are bigger than 5. You would write all of these numbers into the table. So you'd write 45. You'd write 45 in here. It was 45, 45, 45. And you put it in parentheses because the parentheses is what means expected. 45, 45. 45, then 38.3 and 16.7. So this is 45 as well. I think it was 38.3. 38.3. 38.3. This was like 16.7. 16.7. So you write all those, and then you could say, yeah, all the expecteds are bigger than 5. Again, it's supposed to be 80% of them. So you could have one that isn't, because 8 out of 9 is still over 80%. 7 out of 9 is not. So you'd have to get more samples at that point. Okay, no problem. All right, now let's go to run the test. This thing is so incredible. It just does it all for you. We'll do it by hand in class. All these how you get these numbers by hand, we'll do it in class. It's really boring, but you should know how to get this by hand. And the bigger this is, the smaller this is. So this is significant. So then you draw your curve out and label it your chi-square sum. Just label it just like this. And then this is a reject HO. We have evidence to suggest. We have evidence to suggest that the brands have different measures of relief. They're different. Okay, so that's so simple how you do it. So you can learn this all in one day. So among university students, so this is university students. These are all the same kind of people, all university students. So because it's all university students, I'm thinking homogeneity here. Okay, because I'm sorry, I'm thinking, geez, no, what's wrong with me? I'm thinking um I'm thinking in independence, because I'm losing it here. Because it's one population and two traits. Man, one population and two traits. Sorry for the scrolling there. So one population and two traits. So it's all college students. So the traits are what their majors and their drink. Okay. And this will do the exact same thing. So HO, the major is your type of drink is dependent on your major, is independent of your major, and then HA is the type of drink is dependent on your major. Okay. So, and then you're going to throw the numbers in there into Desmos. We'll do that right now. Okay. So 40, 65, 15. I already forgot. 40, 65, 15. Next one is 55, 20, 45. And then the last one is 50, 40, 20. Okay, create test. Get the expecteds first. All the expecteds are bigger than 5. I won't write those out, but you write them out on the test and look, they're all bigger than 5. For the in and spin, you can see that this cell is the most off, has the biggest gap between observed and expected. That's the biggest contributor to the chi-square sum. I've seen the question in multiple choice, which trait or which cell is the biggest contributor to the chi-square sum? I've seen that question. So there's that. Okay. The totals in there. If we run the test, you can run the test. P-value comes out really small. So there's definitely, depending on your major, you definitely order a different type of drink. So there you go. That's the chi-square for tables. The Desmos calls it the chi-square test for independence. but that's pretty much all there is. Everything else in here is kind of a repeat of everything. So, but in one day, you've kind of got it. All right, there we go. So that's it for the first day of chi-square for tables.